Let's now discuss if we may be able to prove these two proof obligation. But before that, I would like to introduce more inference rules to help us, because now we may have to use the implication rule because we got conditional invariance, invariant number 3 and invariant number 4 over here. You can see implication. So we definitely should really expand our repository of example inference rule to really handle these whenever necessary. Let's take a look. And this is just a reminder about what we did before about the proof obligation. So this will be the first one. And if you did the exercise already, you can double check your answer. It's actually over here. So that's the exercise you're supposed to do before you move on to the proof part. And I'm going to talk about 3 inference rules that might be useful for us whenever you got implication involved, either in the hypothesis or in the goal. Let's take a look at them. Okay. And each one of them should be kind of familiar to you maybe in a different shape in your earlier math course. Let's take a look. And let me first of all point out the special syntax over here. If you got P implies Q, the implication to the left of the turnstile, right? So this is something we call implicative hypothesis. Implicative hypothesis. And symmetrically, if you got P implies Q to the right of the turnstile over here, meaning that it's the goal. It's called implicative goal. Of course, they will be handled differently. And don't forget, we also got different rules for handling conjunctive hypothesis or conjunctive goal, and also disjunctive hypothesis or disjunctive goal. So we got all these rules already introduced to you. You want to make sure you're clear about when to use them. Let's talk about the first one. You can see the first one here, implication appears to the left of the turnstile. That's why it's called implication to the left of the turnstile. Don't forget about the naming convention. And this one here nicely corresponds to a rule that you may have seen before. It's called modus ponens. Let's write it down. Modus ponens. And do you remember how to formulate it? If I got P implies Q, and also I have P, the antecedents or the assumption being true, that would be equivalent to just Q. That's modus ponens. Having some implication and P matches the antecedents, the consequence should be the case. That's modus ponens. That's exactly what we're seeing over here. In order to prove a sequence where in the hypothesis over here we got P and also P implies Q, it would be sufficient to prove the following. To say we can simply get rid of this implication structure. We just got the original hypothesis over here and also the consequence over here, and then the original goal should still be proved. So that's the first rule. And you just have to remember it's really corresponding to modus ponens. Right, so hopefully okay so far. Right, let's talk about the second one. For the second one, the implication appears to the right of the turnstile. That's why it's called imp to the right. And this one here is corresponding to some predicate rule called shunting. If you recall from the earlier math course, maybe 1090, you may have seen the rule called shunting. And how can it be formulated if you remember? It's P and Q implies R is equivalent to P implies Q implies R. That's the shunting. You can look it up, but otherwise you can also try to prove it. The way to prove it, the easiest way is to have a truth table and to make sure this is equivalent to that for all the combinations for PQR being Boolean. I'll leave that to you if you're interested. How is this corresponding to our sequence rule? Indeed, it's really corresponding to it. And you just gotta recall. Remember, for turnstile, the formal meaning for that is really implication. Over here, right? You can think about this is indeed H implies P implies Q. H implies P implies Q. That's the right hand side. In order to prove this, where we got implicative goal, it will be sufficient to prove the following over here. And remember the comma over here for the hypothesis is really conjunction. Indeed. So this will be H and P implies Q. This will be P and Q implies R. So that's why we got a nice correspondence over here. You can see that just the syntax is different, but the idea is really not new. But of course, if you forgot about this shunting rule, you can definitely review it to brush up. But if you need any more insights into the rule, reach out to me. So this will be the second one. I think it's really nice to go over such inference rule because you can see they are not something that's completely new. You definitely have the foundation that have been built from your earlier math courses. We got modus ponens, we got shunting, and let's see the last one. The last one here is corresponding to contrapositive, which I believe we review in the week 1 and 2 math review lecture. Let's talk about it. Contrapositive. For the contrapositive, we say if you got P implies Q, that should be equivalent to not Q implies not P. And let me box it, and then we can talk about it to see how it is corresponding to the inference rule that we're introducing over here. Okay. And the rule is called not L. Let's see why. Basically, it's saying that we got some negation is appearing to the left of the turnstile. That's the naming convention, just being consistent. What we're having here is, again, remind yourself that the turnstile over here, the full meaning is imprecation. So what we have is not P, well, thinking this way. Let me try to write it down. This one may be a little bit trickier to see. We basically got not P implies, let me just put it in capital, so that'll be better. Not P implies Q. By contrapositive, what should that be equivalent to? It should be the negation of this implies the negation of that. That'll be double negation, not P, which will be P. That should be not Q implies not P, which will be just P. You can see this part over here is corresponding to exactly the part to really prove, right? In order to prove this particular sequence where the hypothesis is actually a negation, in that case, it would be sufficient to prove to prove this sequence instead, where we simply take the negation of the goal and move it to the hypothesis, and we take the negation of the hypothesis and move that to the goal. That's exactly what contrapositive will do, right? So just make sure you understand this rule in general and see exactly how this particular shape of the turnstile of the sequence is instantiating this contrapositive rule. I think that's something you want to watch out for. Right, let me just highlight it and just make sure you know what to review. Right, so that's about the 3 inference rule that might be useful for us when we try to prove the preservation of the invariants that are specifically conditional invariants using implication. Let's now move on to the proof.